Can you hear me?
Yeah, so we're going to talk about cost instanton and
Yeah.
QQ.
Thank you. So I will try to adjust my talk to the audience requests, if there are any. So, second? Oh, sorry. This one? Oh, this one?
Yeah.
Okay. Oh, good. All right. No exercise. Okay, so I'm going to describe a new construction in gauge theory in 4 dimensions, which may serve to, at least in the PR sense, as a justification of extra dimensions. So as you know, one of the greatest achievements of string theory was to give a sort of explanation of black hole entropy given by Waffe and Strominger by explaining it as a consequence of number of degrees of freedom living on a bunch of d-branes, which would generate black hole effectively. And to have this mechanism, you need extra dimensions for the d-branes to wrap on. So today, I'm going to describe a much more modest construction where you start with 4-dimensional gauge theory. So I'm going to study gauge theory on R4. And this is going to be supersymmetric gauge theory, just because that's where I can compute things. And it will turn out that there are natural observables in this theory, which I will call the QQ characters. The meaning of this term and the motivation will follow, which are natural from the gauge theory point of view because the correlation functions have interesting properties. And it turns out that one way of interpreting these observables is by imagining that in addition to the world volume of the gauge theory we start with, you have an auxiliary gauge theory which would live on a completely different space. If you do the string theory construction, that would be the space which is transverse to the 4-dimensional space you start with, which will have a gauge theory of its own, which will slightly interact with the gauge theory we're interested in. And these observables are obtained by integrating out the degrees of freedom on this auxiliary world. So one cartoon would be to say it will be as follows. So you have the 4-dimensional space with our gauge theory. Let me call this space R4n. And then at some points, you insert extra worlds. So it could be a bunch of stack of parallel worlds, also 4-dimensional, which I will call R4w, on which you have the auxiliary gauge theory. And so the world volume, so these two R4s intersect transversely. So these are the transverse. They're transversed in the A-dimensional Euclidean space, which encompasses these two pictures. And well, in general, of course, you cannot really integrate out all the degrees of freedom because you may have massless fields. But if you make sure that you have some background field such that the degrees of freedom on its auxiliary world volume can be integrated out, you will end up with the insertion of observables, which I will call chi, chi1, chi2, and so on, which represent the degrees of freedom of these auxiliary worlds. Which will depend on some parameters. In particular, there would be the expectation values of the of various scalars. So these operators depend on some parameters, which I will now denote collectively as x. And later I'll specify more precisely what these parameters are. So it turns out that why is it interesting to have this picture and not some other picture is that it turns out that the supersymmetry of this configuration allows for the supersymmetric configurations natural for one gauge theory, like instantons, smoothly transition from one wall volume to this auxiliary one. And you end up getting a recursion relation between correlation functions of these observables and those which are you can relate to them, recursive in the number of instantons.
So these parameters x are relative in R gauge theory?
Say again.
These parameters x that you wrote there for chi of x, these are parameters that are expectation values in R gauge theory and the original gauge theory?
This is, well, there are many parameters there. So most of them correspond to the parameters of this auxiliary gauge theory. And there will be one interesting parameter which describes the which is responsible for how these two theories talk to each other.
But in that case, it won't strictly be an operator of the original theory in any sense, right? If it depends on an expectation value of the original theory.
Well, it's an operator of the original theory which depends on parameters. So from the point of view of our theory, whatever happens in this hidden world, the vacuum of this hidden world are just parameters. They label different operators. OK, so let me make this more specific now, more concrete. This is probably shadowed, right? OK. So let me start with an example. Let's take as our theory well, let's take it to be the NF equals to N SUN superior Mills theory. So this theory has a microscopic coupling constant, which I will sometimes exponentiate. So that's the parameter which counts instantons in this theory. It has 2n masses of the fundamental hypermultiplets. And the vacua of this theory are labeled by the expectation values of the Higgs field in the adjoint representation. So I'm assuming that my fundamentals are massive, and I will deal with UN theory, although U1 will essentially freeze. So there are in addition there are n parameters labeling the vacua of the theory. So this is the sort of the phase space I'll be playing with. And now I want to start by describing my observable. So first, let me introduce a pre-observable, which I will call y of x. So this is naively, this is just a characteristic polynomial of the Higgs field. So phi is the scalar in the vector multiplet. So the natural observable would be to just to take the characteristic polynomial of phi. Phi is the n by n matrix. You can also write it as x to the n exponential infinite sum. So this is sort of a generating function, exponentiated generating function of the single trace gauge invariant operators constructed out of phi. So classically, if phi were just a matrix, this infinite series would, of course, be just a logarithm of the determinant. So the whole thing as a function of the variable x would be a polynomial. However, due to non-perturbative effects, due to instantons essentially, the products of these operators get quantum corrections. So they don't obey the standard multiplication table of Casimirs of the algebra. There are corrections. And so it turns out that if you evaluate this operator in the background of an instanton, this is actually a rational function. So it has degree n. So this leading asymptotics is still there, but it has order of k poles, well, actually essentially square root poles in the background of k instantons. So these operators, if you, well, what would be a good analogy? If you think about the sigma model, the topological sigma model, the analogs of these Casimirs would be the homology classes of the target space, and the product does not obey the standard product in homology. It has quantum corrections, quantum cohomology ring. So if you take this into account, that sort of gives rise to this statement. Okay, so it turns out that this y, and there is a precise formula which maybe I will get to if we really need it. So if you regularize this operator, it turns out to be written not as a single determinant, but as a ratio of determinants of some infinite dimensional matrices, and that's where the poles eventually come from. So for this theory with an f equals to n, it turns out that there is an expression, a composite operator, which is constructed out of this y and these parameters, which will actually be a polynomial of in x. So let me give this operator. In fact, there is a whole sequence of such operators. The simplest one So let me explain the notation here. So P of x is just a polynomial which knows about the masses of the fundamental hypermultiplets. Q is the exponentiated gauge coupling. It's an instanton parameter. And epsilon is the sum of epsilon 1 and epsilon 2. These are the omega deformation parameters. So I want to study my theory to make things really well defined mathematically. I want to work equivariantly with respect to rotations of R4. And so epsilon 1 and epsilon 2 are the two equivariant parameters for these rotations. So the claim is that if you take this observable y, so this is a rational function of degree n, and add to it another rational function of degree n, so the polynomial p has degree 2n and y has degree n, so the degree is conserved, this observable will have no singularities under the expectation value. So if the expectation value of this operator has no poles. The poles which you get in y will be cancelled by the zeros of y which coming from the second term. And as you see, there is this the power of q here. So these poles and the residues between different poles are cancelled between different instanton sectors of the original gauge theory. So this statement that you have a relation between the path integrals in different instanton sectors can be viewed as a sort of discrete version of a Dyson-Schwinger relation, which is usually stated in the continuous in the continuous case. So it's a statement that the expectation value of in quantum field theory with the action S of the equations of motion can be reduced to the expectation value of fewer operators. So this is obtained by the integration by parts and follows from the invariance of path integral under infinitesimal variations of the contour of integration. Here I'm stating something which corresponds to a discrete change of the path integral contour, something like the grafting of a point like instanton. So I'm changing my gauge fields by adding a small instanton somewhere. So this is not. So this is the something which I call the fundamental QQ character. So first of all, why is the word character in this story? Well, if you look at this formula from far away, you see the structure that the way I assembled my terms was that I took this observable y and then added something like 1 over y with a coefficient which was simple. So this should remind you a trace in the two-dimensional representation of an SL2 matrix. So this is something like y over square root of p over y, square root of q, square root of q. So so the structure of this formula, it's in order to appreciate it, we will look at other cases, more general cases, but somehow it suggests that this theory has something to do with SL2. So this is the trace of an SL2 group-like matrix in a two-dimensional fundamental representation of SL2. So this is why it's called fundamental. And it's a QQ character because it's actually double deformation of the standard character, of the usual character of the group SL2. So this double deformation comes from these two epsilon parameters. In fact, as you see it, look at this formula, you only see one combination of the parameters epsilon 1 and epsilon 2. This is because we're looking at the fundamental character of the A series. If I give you an expression for the general QQ character for this theory, so this theory is also known as a theory of A1 type. I will explain later why is it so. So A1 corresponds to SL2. So the more general observable depends on the number W, and W complex numbers nu. So the generalization of this operator will depend on, again, I'm interested in the function of x, but it will depend also parametrically on w parameters nu. And the formula is the following. It's a sum over all ways of partitioning the set of w elements into two disjoint sets, q to the power the number of elements in the set J, product times certain S matrix-like factor, which depends separately on epsilon 1 and epsilon 2.
Just to make sure I understand.
Yes.
So why you started the definition as a determinant of x minus 5?
Regularized determinant.
When you say regularized, why does it need regularization as a Carl field?
Yes, it's a Carl field, but so you need to define properly what trace of phi to the n means.
Well, just orient myself. Take
Okay.
a SU2 case.
Yes.
That's just phi squared minus x squared or something like that, right?
No, it has not quite. It's I define it as exponential of trace phi squared over x squared plus trace phi cube over x cube and so on and so forth. So trace phi to the fourth, for example, for the 2 by 2 matrix is equal to trace phi squared over 2 maybe. But as an operator in SU2 gauge theory, it is not. So if you go back to the old,
You want to say that the truncation will give you Q character, but why should it be singular? There's no singular. Where do you get singularity?
well, if you well, it's an infinite series. So a priori, if there is no if the relation like trace phi to the 2k is trace phi to the square to the k over some factorial is violated, if you add additional terms, then the series will sum up not to just logarithm of a polynomial, but it will be logarithms of polynomials which go in denominator and so on and so forth.
So you're saying it's because of the Chiral ring that it has.
Yeah, it summarizes the Chiral ring relations.
But Chiral ring, isn't that in some sense simple in these theories?
Well, it's well. First of all, even if you take the limit epsilon goes to 0, so go back to the flat theory. So the formula which we'll get would be that y, this y, plus q it's a degree n polynomial. So this is known as a Zabir-Quinton curve. So if you extract y from t is an honest to God polynomial. So all the chiral ring relations you're referring to are contained in this formula. But if you now do the series expansion at infinity of y, you will see that the coefficients do not obey this relation. They're much more complicated. So in particular, well, let me write a formula which you remember. Trace phi to the k in this limit is the sum over the A cycles of the Zabir-Quinton curve. So you see, this is it is by no means it's not a k power of trace phi squared. So what I'm describing is the sort of microscopic derivation of that with epsilon parameters and so on.
These are not going to surface operators?
No, these are point-like operators. So these are, for the moment, these are operators which are point in R4. Yeah. We'll get to the surface operators if time permits.
So this quantum chiral ring relation, how are you going to derive it? Just from the Zabir-Quinton curve?
No. This is the completely reverse logic. Zabir-Quinton curve follows from these relations.
Follows from the quantum chiral ring.
Yes, it follows from the statements which I'm making. So my main statement is that the expectation value of this observable Again, you see, there I have lots of y's, lots of 1 over y's, and y's are rational functions, as I said. So in a given instanton background, this expression has many poles. But the claim is that these poles will cancel after you've summed over all instantons. And well, actually, for this theory, you can prove this statement just by hands, by evaluating the residues and checking that they cancel. And you can generalize it to A-type quivers, and again, check it by hands, because with omega deformation, the path integral in these theories would just become the sum over the lots of partitions. And so for a given, well, maybe that will be helpful. Let me show you the expression for this observable in the background of instanton, which is rotationally invariant. So then, remember that this rotationally invariant instantons correspond to n-tuples of Young diagrams. So these are n-tuples of partitions. So evaluating y on such an n-tuple, where C of the box, it's a content, so-called content of the box. It's a linear function of epsilon 1, epsilon 2. Mathematically, this follows from this occurs because we modify the path integral from the integral over the space of ordinary instantons, ordinary gauge fields, or holomorphic bundles. We replace it by the integral over the modular space of torsion-free sheaves. And so trace phi to the L becomes the Lth Chern class of rank n sheaf, which is not a bundle in general. And so the relations between Chern classes of sheaves are not the same as relations between Chern classes of bundles. And this is where these poles come from eventually. But the claim is that if you arrange these y's in such an expression, then all the poles will cancel. So this should be viewed as the, so this is a sort of quantum deformation, like a secondary deformation of the Q character of the Youngian of SL2. So the representations of the Youngian are labeled by the highest weights of the representations of the finite-dimensional algebra, and also continuous parameters like evaluation parameters. So this should be thought of the trace of in the representation where you have like a tensor product of spin 1/2 representations. Inserted at the points nu1, nu2, nu w of the Youngian. But this is more general. I mean, this is yet deformed. So the Youngian you get if you send one of the epsilon parameters to 0. And this algebra, I don't really know what is the algebraic structure which you get with all epsilon parameters present. Okay, so let me give you one more example, and then I'll reveal the mystery of these formulas. So another theory which we all like is the so-called n equals to 2 star theory. So this is so n equals to 2 star. In this theory, so it's gauge group UN. You again have the microscopic coupling, and you have only one mass parameter, m, mass of the adjoint hypermultiplet. So this theory is called the theory of the type A0 hat. And again, you have the scalar and vector multiplet. So the fundamental character for this theory, well, this hat suggests that the hidden algebraic structure behind this theory will have to do something with Kac-Moody symmetry. So the character you expect to be an infinite sum. And indeed, this is what it is in this case. So the formula is the following. So this is going to be the sum over a single partition. And then each partition will contribute certain weight, b lambda, which I'll specify later. And then you have a product over all boxes of the Young diagram of the partition, y where here, so in this formula, I had the content which was denoted by letter C of box, which was the linear function of epsilon 1 and epsilon 2. And in this formula, I have another letter for the content. So here, the content of the box with the same coordinates I and j is equal to m times I minus j plus epsilon times 1 minus j. And b of lambda is some rational function of m at epsilon. So actually, by looking at this formula, it is by looking at this formula that you may get a hint at what is the origin of such relations. What this formula suggests is that you have an auxiliary U1, in this case, n equals to 2 star theory, which lives on R4 with omega deformation, with different omega deformation parameters, with parameters which are m and negative m, negative epsilon. So our theory lives on R4 with the omega deformation parameters epsilon 1, epsilon 2. And this formula, so this observable, is obtained by computing the partition function of U1 n equals 2 star theory on a different R4 with these equivalent parameters, with some observable which couples both. So y is the observable of our gauge theory, but the argument of this observable y is shifted by the by the eigenvalues of the Higgs field of this auxiliary theory. So these contents, just like here, the contents with parameters epsilon 1, epsilon 2 know about the spectrum of phi. So they enter the, so maybe one way of explaining this formula is to say that effectively the phi, which starts as the n by n matrix, becomes, in a sense, a supermatrix. So you can view this as the characteristic polynomial of a supermatrix of the size n plus k, where k is some large number, depending on the, well, roughly 2k, roughly twice the instanton charge. And so the eigenvalues which you see here, so there is the excess n eigenvalues which are equal to the old Coulomb parameters A alpha, and then there are pairs of eigenvalues which go both to the even and odd parts of this matrix, which know about the contents of the boxes. And so here what you see the similar structure, but now the contents have different multipliers, m and epsilon instead of epsilon 1, epsilon 2. So what is this? So, these measure factors precisely to correspond to the n equals to 2 star theory. So what does so? So one way to interpret this formula is to say that mathematically is to say that there is a moduli space which is labeled, so for this theory, for the theory A0 star, and for the theory A1, so for these moduli spaces are slightly different. So let me first describe the case of A0 star, and then I'll explain the A0 hat, and then I'll explain the modification for A1. So there is a moduli space of some objects, which is what I call the crossed instantons. These are, roughly speaking, these are instantons on the which live on the cross. Oops, sorry. So the quaternionic cross. So it's a Q, bad notation. Z1 bar, Z2 is equal to 0, or maybe Z1, Z2 equals to 0, where Z1 and Z2 are quaternions. So this is the thinking about the analogous construction for the stable maps, where for stable maps you generalize the notion of the holomorphic map of a smooth curve to the curve which has nodal points. So think about the stable maps. Of a curve which has the double point. So locally this curve is described by this equation. So now what I want to have a generalization, sort of a quaternionic version of this construction, where I'll have two quaternionic lines which intersect transversely. But the novelty, which is suggested by these formulas, is that the gauge group of your instantons can be different on different branches. So I will have UN gauge group on the blue branch, and UW gauge group on, we call it the green branch. Well, it turns out that there is actually a nice modification of the ADHM construction, which would which describes these objects. And the nice feature of this moduli space is that it contains the ordinary modular space of instantons, so this M and so if you have an integral over this combined modular space, and some kind of localization expresses this integral as a contribution of these subvarieties, you will get a relation between the integrals of an instanton modular space in four-dimensional theory, which is what we're interested in. And so,
The dimensions match on that, right?
so the dimension is an interesting thing. So this is actually okay. So this is a singular. It's actually a singular manifold, singular variety, and its expected dimension is actually k independent. Is equal to -2, if I'm not mistaken, n times w. So what does it mean? First of all, what does it mean to have a manifold of negative dimension? What it means is that you may have a component of positive dimension, but this component comes with the abstraction bundle of even higher rank, such that the difference between the dimension of what you see as the actual deformation space and this number of abstractions is equal to this difference. So these spaces are smooth if you turn on the B field, so which is what I'm doing explicitly in my story. But they sit inside, on top of these smooth manifolds. Each component of this type comes with certain bundle on top of that, which compensate the excess in dimension. Let me explain this maybe in a language which might be more familiar. Remember in the story of Kumun and Witten on S-duality, making this strong complex test of S-duality in 1994, they were looking for an interpretation, for the mathematical interpretation of the partition function of n equals 4 superangles theory, appropriately twisted. And they found that unlike the pure n equals 2 theory, which computes, well, in the absence of observables, will give you normally 0, but if you have observables of appropriate type, gives you Donaldson theory, so just the theory of integration of an instanton modular space. In n equals 4 theory, the additional fields which you have in the vector multiplet of n equals 4, they provide an integral representation of the Euler class of the tangent bundle to the modular space of instantons, if you have the vanishing theorem. So these additional fields is what essentially this is what my bigger modular space has. It has this, I think what Greg Moore called the cofields. So you have the auxiliary multiplet which generates for you the Euler class of the tangent bundle. So this is a nonlinear version of that. So namely, if you're sitting near the locus where so for w equals to 0, so even for w which is equal to 0, actually this modular space differs from the ordinary instanton modular space. Namely, as a bosonic, so it will have a bosonic component which will coincide with the modular space of ordinary instantons on R4, but this modular space also has the abstraction bundle, which will turn out to be the cotangent bundle of the modular space of instantons. So if you compute the integral of 1 over this moduli space with W equals to 0, that's actually computing the Euler class of the tangent bundle over the moduli space of instantons. So in this case, the expected dimension is 0 when W equals to 0. So of the varieties of dimension 0, you expect it to be able to integrate 1. So just to count number of points. So this is what n equals 4 super-Yang-Mills was supposed to do. It was supposed to count the number of instanton solutions if these solutions were discrete. But since they're not discrete, this counting becomes the computation of the Euler class. So what my modular spaces do, they generalize this for any W. And that should be compared to, again, in the case of the stable maps, to the fact that if you want to study the maps with marked points, for each number of marked points, you have a different stability condition and a different modular space. So this W is to be thought of the sort of the number of marked points in the Gromov-Witten theory case. So there is actually a very nice ADHM-like construction for so ADHM like construction. So you fix 3 vector spaces, capital N, capital W, and capital K. These are vector spaces of appropriate dimensions, N, K, and W. And now you have, so in the ordinary ADHM construction, you have 2 matrices which in this notation will act in the space K. And then you have matrix I, which acts from N to K, and the matrix J, which acts from K to N. So normally you impose this equation. So this is the ordinary ADHM. And then divide by the action of the group GLK, or you impose the real moment map equation. So if you set this to 0, then this gives you the Uhlenbeck compactification of the instanton modular space. And in order to make my story smooth, you actually set this to be equal to a scalar matrix with some parameter zeta. So if zeta is not equal to 0, then this modular space is what I call M curl M of nk. Now I'm going to modify. So now I introduce additional matrices, which will be the B3 and B4, which also act in the space K. I have matrix I tilde, which will map W to K, and J tilde, which maps K to W. So now I'm going to marry these 2 constructions. So I write the ADHM construction for B1, B2, ADHM moment map for B3, B4, and then take Hermitian conjugate and set this to 0. And then I'll add to this the real moment map with the other matrices. Of course, now that I have many more more matrices, I need to impose more equations. So this is just the beginning. I have Say again?
Do you have a quiver description?
So this is, for the moment, I'm doing this for the simplest possible quiver. So this construction corresponds to the quiver A0 hat. So just one vertex, one loop. But of course, once I'm done with this, I will explain how this is generalized to any quiver.
I mean ADHM quiver.
This is the ADHM quiver. So this is the condensed notation for the ADHM quiver.
When you modify, do you have a quiver that you modify with?
This is the modified ADHM construction for this quiver. It's a shorthand notation. Yeah. Well, you will see why. It's okay. So I have additional equations which tell me how 1, 2 talks to 3, 4, and so on and so forth. So it will be equation like that. So now I have imposed, actually, if you count the number of equations which are square equations, that's the same number as the number of degrees of freedom. And I also, so I have 3 real equations between, between these 2 lines, and 2 more complex equations, or 4 real equations. So I have in total 7 Hermitian equations, K by K matrices. And I start with 4 complex matrices, which are 8 real matrices. And these equations are UK invariant. So that takes care of all the square degrees of freedom. And the novelty, which of course it's not novelty actually, if you, again, as I said, if you go back to 1994 paper of Waffo and Witten and try to implement this construction at the level of the ADHM data, you will actually come up with the B3, B4 matrices, just that we didn't do it before for some, I don't know why. So B3 and B4, from the point of view of the original ADHM, B3 and B4 are the cofields for this construction. So now there are additional equations. These equations guarantee that, they sort of guarantee this picture, that namely, if you go out to infinity along the blue component, and so the asymptotics of the gauge field, of the UN gauge fields in the ADHM construction, is governed by the matrices I and J. So what we want is that if we are out at infinity here, then from the point of view of the blue component, of the green component, we are at the origin, at 0. And so this is what guarantees it. So it says that, more or less, that whenever I and J are non-trivial, when the instanton is colored, has non-trivial asymptotics, then B3 and B4 beta vanish. So it means that, so B3 and B4 are coordinates in this direction, and B1 and B2 are matrix coordinates in this direction. And symmetrically, there is a similar equation for I tilde. So, and finally, there is one last relation, which is what makes this space of negative expected dimension. It involves I and J only. And sometimes it is convenient not to impose this equation. Then you get a space of virtual dimension 0, actually.
So nothing comes for no extra field is needed for a map from N to W.
So this equation takes values in maps from N to W. So this is how you count for it, actually.
No extra field.
No extra field. So these extra fields, they
Oh, they okay. Linear appear, so the equation of motion of them.
Yes, that's right. That's right. So of course, once I drew this picture, you can have a D-brane picture in mind, of course. And of course, so this has to do with the modes, which are the 4/4 strings. But that's not the way this picture was invented. So this is backward.
Just if I look at the graph project this onto any linear subspace other than those two color lines?
Sorry, project.
I can think of your two special line projections of this bigger function.
Well, it's not a projection. It's embedding. You see, these instantons, then they don't extend to the 8-dimensional space. They support it either here or here. Okay, so it's not. All right, so let me now explain about quivers, because my time is short.
Sort of in the same way, can I think of Stickman segregating curve instead of the product?
No.
So one of the theories is that it doesn't have its own curve.
In order to discuss the curve, you need. Okay, let me make one more step. So we're not there yet. I need to discuss the symmetries of these equations, because the symmetries are responsible for the omega deformation, and then you can see at some point. I mean, eventually you will see whether the curve occurs when you send the parameters of omega deformation to 0. But you will see that this setup is such that if on one component you are approaching the flat space, on the other component you actually have strong omega background, unless you are in the n equals 4 theory, which has trivial curve. Okay. Anyway, so if z is equal to 0, then these equations have a triple SU2 symmetry. So one SU2 rotates B3 and B4 as a doublet. Another SU2 rotates B1 and B2 as a doublet. And so this is the first one, let's say what was 1, 2, and this was 3, 4. And then there is the third SU2, which simultaneously does something to B3, B4. So in fact, it rotates B3 and B4 dagger as a doublet, I and J dagger as a doublet, and B1 and B2 dagger as a doublet. So SU2, 1, 2 preserves the complex structure on B1, B2 space. SU2, 3, 4 preserves the complex structure on B3, B4 space. And this diagonal SU2 simultaneously rotates the complex structures on these two spaces. Now, when I turn on zeta, so it breaks this diagonal SU2 down to U1, but it's still U1, so you can still use it. So when we do the omega deformation, we can turn on the maximal number. We can turn on the 3 parameters, because the rank of this group is 3. So there is U1, 1, 2. So this is, let's say, epsilon 1 minus epsilon 2 over 2. This is epsilon 1 plus epsilon 2 over 2. And this is essentially the mass, which I shift by epsilon 1. Maybe that's the way to view this. So the 3 parameters are 2 epsilons and the mass of the adjoint hypermultiplet. So now, what happens is that if you send the omega deformation parameters for our gauge theory to 0, then for this gauge theory, you still have parameters m, negative m. Okay? So this means that you are still at a free fermion. Oh, but the mass, the mass of the adjoint hypermultiplet, which this theory sees, is epsilon 1. So that goes to 0. So if you want to see the Zabel-Rutten curve for this theory, you're actually dealing with n equals 4 auxiliary theory with omega deformation. And in this limit, this QQ character, which I wrote, becomes the Kac-Moody character, which is, and so you'll get lots of elliptic functions, and that's why the Zabel-Rutten curve for the n equals 2 star theory is written in terms of elliptic functions. I mean, this is very rough picture. Of course, the whole story is much more precise. Now, once you have this SU2 cross SU2 cross SU2 symmetry, you can choose a discrete subgroup of SU2. And in fact, well, if zeta is non-zero, which is where things are nice, you have a choice of up to 2 SU2s, up to 2 discrete subgroups of SU2, or actually you can actually make them subgroups of U2 because there is this U1. And so you can orbifold. You can subject this construction to orbifold construction. And in particular, in this way, you can get the theory for all affine quiver theories. So this story will get modified. The roles of matrices B1 and B2 and B3, B4 will be different. So it turns out that this modular space for the quivers will now contain the products of the modular spaces of instantons in quiver gauge theory cross Nakajima varieties for the same quiver. And so these QQ characters, in general, are written as integrals over these Nakajima varieties of some expression which is constructed out of the Y observables. And finally, the main point, which, well, I will just state in words, why is this existence of this modular space of crossed instantons is useful? It's because, well, even though it's a singular variety per se, but it is smooth in the derived sense. So you can stratify it into components, or which component you have you have a smooth component with constant rank abstraction bundle. So this these bundles glued together over the intersections of the strata. And the point is that the set of fixed points for a certain U1 symmetry, so there is this U1 symmetry which, so I did not discuss, I discussed the rotational symmetries of these equations. But in addition, of course, there is also UN cross UW symmetry, which acts in an obvious way on I and J, I tilde J tilde. Now, normally the U1, the center of each of these UNs for the ordinary ADHM construction acts trivially because it's a part of the UK group we divide by. But now you have two U1s. And so one of them is eaten up by the U1 inside UK, but the relative U1 acts non-trivially. And so the relative U1, this corresponds, the corresponding Coulomb parameter or the corresponding equivariant parameter is the variable x of my observables. And the claim is that the set of fixed points for this U1 relative symmetry is always compact. And so it means that for any value of the equivariant parameter for the symmetry, the integral which we're computing essentially the integral of 1, is finite. And therefore, the total integral has no singularities in x. OK, so I'll stop here.